Right, good evening, everybody, and welcome. And welcome to all those online as well. We've just finally managed to configure, get everything going, I think.
So good loss.
We'd like to welcome Ross Skelton, who is the big boss of South African Astronomy. What is your title? Director?
I'm managing director.
Managing Director of SAAO, South African. So she is nobody better than her to give us the lowdown of everything that happens at Sutherland and all the other things that SAAO works with. So we're looking forward to a very interesting talk, direct from the horse's mouth, so to speak. All right.
Thanks.
No insult intended.
Thanks. Good evening, everyone. Thank you for having me here. It's very nice. This is my first visit to the Hermanus Center. So it's great to be here in person and be able to share with you what we're doing at SAAO. Many exciting projects that I hope I'll give you a flavor of tonight. So our aim at SAAO is to explore the universe for the benefit of society. And I hope also the societal aspect of that will come through in what I talk about, although I do get excited about the science. And so hopefully you'll hear a bit about the astronomy and the science we do, but also about how we want to impact on South African society. Let's see. So SAAO, the South African Astronomical Observatory, is now more than 200 years old. We celebrated our 200th anniversary in 2020, unfortunately, in the midst of COVID. It's the national facility for optical and near-infrared astronomy, and we fall under the National Research Foundation of South Africa. So our headquarters are in Observatory in Cape Town. The suburb is named after the observatory, and our telescopes are about 370 kilometers away near Sutherland in the Karoo. So the main things that we do are world-class research. We are a research organization as well as providing the platforms for other astronomers around the country and globally to do research. So we provide the telescopes and data. We are also very involved in teaching and training. So the next generation of scientists and engineers, many of them we hope will come through SAAO or be associated with the SAAO in the course of their training. We need to also build instruments and develop the technologies for the telescopes. So most of the instruments on telescopes are not bought off the shelf, though a few modern ones are. But mostly we have to actually make the parts ourselves, design and manufacture them ourselves. And so we have an instrument division at SAAO that is responsible for that. And throughout what we do, we want to try and share our science with society and inspire society and involve younger people in the exciting science that we're doing and use astronomy as a sort of gateway subject for STEM. Science, technology, engineering, and mathematics. Just to give you an idea, I'm sure many of you with an interest in astronomy know about this already, but to give you an idea of what I mean by optical and near-infrared astronomy, these are images of a galaxy at different different wavelength ranges, so through different filters, if you like, going from the radio on the side to infrared to the optical, ultraviolet, and X-ray. And you can see the same galaxy looks quite different depending on which kind of goggles you're using. So at SAAO, we concentrate on the optical and the infrared, so infrared being redder wavelengths than what we can see with our eyes. And the best way to study astronomy or to study astrophysical phenomena is to actually combine the information from all of these different wavelengths together. And that's why it's so important that in South Africa that we have the Meerkat radio telescope, the optical and infrared telescopes based at Sutherland, and we can combine that information with ultraviolet, X-ray, gamma ray data from satellites or from facilities like HES in Namibia. So here you can see our Meerkat radio telescope, which is further north in the Karoo. Some of our SAAO telescopes with the beautiful Milky Way stretching overhead and the Magellanic Clouds. And the HES telescope, which is in Namibia. And that's a high energy, it's called the high energy spectroscopic system, and it detects the radiation in the atmosphere caused by high energy particles coming in. And that gives us this multi-wavelength pick at first click. But anyway, so in Sutherland, we have our telescopes, and you can see here in this drone view that we actually have a lot of telescopes, about 20 or 25 different experiments up on the plateau. They range from SALT, the Southern African Large Telescope, which is the biggest one there at the back. And then we have our 3 SAAO telescopes, actually these 2 and this one, the 1.9 meter and 2 1 meters. We have Meerlicht, which is a 65 centimeter one that tracks where the Meerkat radio telescope is pointing. So it's always, if the weather is clear, pointing at the same patch of sky that we observe with the radio. And then we have a new one, which isn't even on here, called Prime. And I'll talk a little bit more about Prime a little bit later. The other one I'd like to point out is called Atlas. And Atlas is an asteroid tracker or a detector. So that finds things that are moving in the sky. It's got a wide field of view, and it captures images every few seconds and basically looks for things that are moving. So in addition to all the telescopes, we have very strong infrastructure up there. We have very good internet connection. We have a hostel where astronomers can stay. We have houses on site where the technical staff live. And that's really why many of the international facilities have chosen to work with us and host their telescopes there. So many of these telescopes are international partnerships, and either fully owned by an international partner, and South Africa has a data sharing agreement with them, or co-owned with us. SALT, here you can see the mirror of SALT. It's an 11-meter mirror. So the diameter of this mirror is 11 meters across, made up of 91 segments. And I'll talk a little bit more about SALT as we go. I mentioned that we put a lot of effort into training and teaching. So that's part of our research. Our students are actually responsible for much of the research that's done at SAAO and in the country. We're part of the National Astrophysics and Space Science Program. It started in about 2003 at UCT, and then expanded to 2 other nodes, one at Northwest University and one at UKZN. It's over that 20 odd years or so, it's graduated more than 700 students in honors and masters. And SAAO has played a big role, not only in leading the program from the beginning, trying to create that partnership that was really important, because there was not, back in about 2000, there wasn't a critical mass of astronomers anywhere in the country. Cape Town was the biggest hub, and so SAAO played a very important role in setting up the program, but we still play an important role in teaching courses and supervising student projects. We usually host about 5 honors students a year at SAAO doing their honors project, and roughly 20 to 30 MSc and PhD students. And they're usually they spend some time at SAAO and some time at their university where they're registered. Many of them are registered at UCT or UWC in the Cape Town region, but we also have students registered at Northwest and other universities. And we try to give them hands-on experience in observing, but also in the outreach that we do in the instrumentation projects, so they get an overview of all the different parts of astronomy. In terms of research, we produce about 120 papers a year, or co-authored papers with SAAO-affiliated authors. So we make a good contribution to the astronomy efforts worldwide. And we have a lot of partnerships, some of which I'll talk about as we go. We've just launched last week what we call our Remote Operations Center. It's been going for a few years, but we took the opportunity last week of the Minister of Science, Technology and Innovation's budget vote in Parliament, and then he came to SAAO afterwards and launched our Cape Town Visitor Centre and this Remote Operations Centre. So this is a place where we can connect from Cape Town to the telescopes in Sutherland, and we can observe with the telescopes in Sutherland from Cape Town. So this just gives us much more flexibility in the way that observing is done. It means that we can train students in Cape Town, and we can allow the public to also come and visit. That's our sort of flagship Remote Operations Center. We also are working on artificial intelligent observatory, which is using AI, artificial intelligence in astronomy. So both for operations, but also looking at how it can be used for the science we do. And I'll talk more later as well. Our other technology developments, fiber lab, where optical fibers, so fibers that take light, can be used. And we have what we call the Precision Fabrication Center, which is a mechanical workshop that produces parts to very, very high precision. And not only for astronomy, but also for Itemba Labs, the Nuclear Physics Institute. And the idea that we're working on is to expand the space we have for technology and a hub where the different national facilities of the National Research Foundation, people can come together and work on projects that might have spin-offs outside of the sciences we do, spin-offs for broader society. So here are a few images just showing you a bit more about our technology. So these are the kinds of parts that we can produce with machines like this. This is a very high-tech CNC machine that we bought last year. And here you can see some of the optical lens that we work with and the sort of mechanical design engineering that goes into these parts. So in terms of our science engagement and impact on society, we have our 2 visitor center, one in Cape Town, which was launched last week, and one in Sutherland. Been going for many years now, and it actually is in dire need of an upgrade. So I'm not sure if any of you have visited Sutherland recently, but it's a space where we can, tell the public about what we do and introduce our telescopes. And we're hoping to improve the exhibits there and also incorporate that multi-wavelength aspect, have perhaps one of the radio dishes or at least an exhibit about the radio dishes there. We have regular public tours and open nights. In Cape Town, we have open nights every 2 weeks on a Saturday evening, and that's been going for many years. But now with our new visitor center, we've also launched tours in between. So every Saturday and also during the week, people can come and visit and do a tour, do stargazing if the weather's permitting. We have a big schools program. So a number of schools come and visit us at SAAO, either in Cape Town or Sutherland. But we also have 2 various schools around the whole country and do teacher training. So they train the teachers on how to teach astronomy, how to do the Earth and Beyond curriculum. And we provide guidance on careers. We're involved in exhibits at various career fairs and expos. We have what we call the SALT collateral set up at the start of SALT, not only to do the school work, but also to engage with the community and try and make a difference to the very poor community of Sutherland. So we have a number of donation drives. We have a community center, which you can see here in Sutherland, which has about 20 computers donated by the Department of Science, Technology and Innovation for the local community to access the internet and work on a computer if they need to. It also has cubicles where the local school children can come and do their homework after school. In their houses, they may not have space for that. Overcrowding is a problem, so they have a safe space where they can come and work. And there are a number of, there's also a creche that runs from there and a number of other programs that run from the community center. We also host the Office of Astronomy for Union Office, both to the International Foundation of South Africa, and they run projects to look at how astronomy can be used for development. So this, to me, and that includes things from education to inequality to things like astrotourism, even looking at how astronomy can be used to improve people's mental health. So quite a number of interesting projects that the OAD runs. These are our 2 sites, Cape Town and Sutherland, and the Meerkat telescope is further north. The Sutherland site is very dark. Here you can see why we had to go to Sutherland. So already in the 1960s, they realized that Cape Town was not a place you could observe from anymore. Suitable site, and settled on Sutherland. It's got reasonably clear weather year round, so it's not too and it's actually about the fourth darkest observatory, and we really have to take advantage of that, but also strive to maintain that. And that can be a challenge. There's a lot of development with wind farms in the area, mining, in the Karoo. And so we have to work quite hard to maintain. We put up very massive lights at the clinic. And so it's a constant battle, but also something that the government is very committed to maintaining, that astronomical advantage we have. And so we're lucky. What it looks like, you saw an image earlier, is this is the 1.9. Three older domes and many other smaller ones. I won't go through the list, but just to give you an idea, there's Ison, but the others are all they all operate at night and look at the optical and the near infrared. The SALT is our flagship facility. It was inaugurated in 2005, so we're celebrating 20 years this November. Largest mirror in the Southern Hemisphere still, until we're overtaken by the extremely large telescopes, which is not going to be too far away, but for now, we're the largest. It's a consortium of international partners. So here you can see some, all the partners. There's the National Research Foundation of South Africa, which is the majority shareholder. The NRF holds about a third of the shares of the telescope, but South Africa contributes half the operating costs. So as some of the smaller partners have the and maintains half the operating costs. IUCA, which is an Indian institute, a few different universities in the US, and a Polish consortium, observatory in the UK, all partners. Anyway, SALT it's been in regular science operations since 2011. So it took a few years to sort out some of the teething issues. There was a problem back in the beginning where the tracker on top was getting distorted. Some calculation had been incorrect, and it took a while to figure that out. So regular science operations started in 2011, and it's been operating really well since then. It's what we call a fully Q scheduled telescope. So that means that the partners around the world, they all submit their proposals every 6 months. They add the observations to our queue, and we observe them. We have a team of astronomers here that does the observations for them. So no one has to travel in from elsewhere around the world. We send them their data the next day. And it also means that it's very flexible. And if the weather is bad, the telescope is shut. It doesn't, someone won't miss out on their data because that was the only night that they were scheduled. The observation will just go back in the queue for the next clear night. So unless there's something that's time critical, that's a big advantage with this type of telescope. The main instruments on SALT are the Robert Stobie spectrograph, which is a general workhorse instrument that can actually do many things, including polarimetry, imaging, and spectroscopy. Then there's a high-resolution spectrograph and the SALTI camera, which is an imaging camera that we mainly use for our acquisition, for finding out where we are on the sky and making sure we're on the right target. Recently, there's also been a near-infrared instrument added. So this is the near-infrared spectrograph. Here you can see it's in a kind of plastic tent within a cold room in the basement of SALT, so to be very, very cold in order to detect the light, the near-infrared light, which is also known as heat. So it's kept really, really cold so that we can see that near-infrared light. It was installed a couple of years with the detector. Many of the detectors made, I think, in about the sort of 2010 era, they realized later shouldn't be stored at room temperature. And so storing it at room temperature, which was the standard, led to a lot of defects in the detectors made at that time. So unfortunately, we have a detector that's not ideal. It's got a lot of bad pixels, and we're trying to figure out now how to work around that, whether we can still get something useful out of it. Otherwise, we're going to have to replace the detector, which is a significant cost. But if we can get it to work, then it'll enable us to expand that wavelength range that we cover. At the moment, we're just an optical telescope. We'll move into the infrared as well. And the other really nice thing about NEOLS is that it's a fiber-fed integral field unit, which means that it's got a whole lot of optical fibers that carry the light down from the top of the telescope to the spectrograph. And here you can see all of the fibers sort of lined up. And that means that you don't observe one source, say at the middle of this array of fibers. You don't just observe one star, but you can observe a whole galaxy and get information about the whole galaxy, the spatially resolved information. So here you can see an example of what that kind of IFU data would look like on a galaxy. So each of these little circles is the fiber that's picking up the light from that part of the galaxy. And so instead of just observing the center, you could observe and we're also expanding that IFU technology to the optical so that we can have simultaneous optical and near infrared. And these here are what those IFU fiber bundles look like in our work or spectrograph, the RSS. So we've recently made these IFUs for RSS. Another recent development, well, it's currently being built, is called the laser frequency comb for the high resolution spectrograph, all the little optical pieces of the laser frequency comb. And what the laser frequency comb does is basically make a ruler out of laser light that you can use to calibrate your data. So in the past, you would have to shine some kind of arc lamp into your spectrograph to see where the arc lines were and use that to calibrate wavelength. Now you can have these laser rulers and you'll know exactly what the wavelength is for each pixel across your telescope, across your detector image. And that'll enable much more precise calibration planets. So planets around other stars, you need to be able to know the wavelength very precisely. And this will enable us to detect planets sort of similar to Jupiter mass planets around other stars. So here you can see just a little sketch of a star with a planet going around it. And that planet causes the star itself to wobble around its center of mass. That the planets, if they're heavy enough, can make their star move. And it's that starlight, as the star, its light is blue shifted or red shifted, and we can detect that slight change in wavelength. And that's how we can infer the presence of a planet. So that's a very exciting development. The Heriot-Watt team from Edinburgh is coming out again in October to finalize the LFC. And then there'll be a bit more work required on the software side, but we hope that we'll put that into operation next year. The other thing that's being done and developed in-house at SAAO is upgrading the detector of the RSS. So currently it's 3 CCD chips put together in a mosaic, and we're going to upgrade it so it's just one big chip, and SAAO is building the cryostat for that. Okay, these are our 3 SAAO telescopes, 2 1-meter telescopes and the 1.9 meter. The 1.9 meter is our oldest telescope. It was the mirror was built in the 30s and then buried underground during the war. and then shipped out to South Africa after that. So that's our oldest telescope, but it's been upgraded over the years and now can be completely robotically controlled. So we can operate it from our remote operations center in Cape Town, and it's part of our Intelligent Observatory project, these upgrades that allow us to control all of our telescopes remotely. So the idea with the Intelligent Observatory is firstly to modernize the older telescopes, to make them remotely operable, robotically operated. So you would be able to have an alert from a telescope anywhere around the world, maybe in Chile, that alert the telescopes to follow it up automatically, depending on what it was, the appropriate telescope and instrument to follow it up. And so that's what we're working towards. The idea is to use the new tools like artificial intelligence and machine learning to make that possible, and to connect the telescopes into a network so that you can choose between any of them, or telescopes elsewhere in Africa or around the world. So the first stage of the project was really upgrading the telescopes themselves, upgrading the telescope control systems. Recently, we've installed a selector port on the 1.9 meter, which lets you between the 3 different instruments. Well, not so long ago, it took about half a day of technicians up there manually changing the instrument on the back of the telescope. Now you can choose between the instruments at the press of a button. So that's all part of the Intelligent Observatory project. And another recent exciting development is a collaboration with the Hartree Centre in the UK, who are specialists in artificial intelligence. So they're working with us to try and see how we can incorporate those tools into our workflow. This is the new kid on the block, Prime. It's a 1.8 meter near-infrared telescope. We had the official opening in January this year. And then it's a Japanese telescope. And this is the older Japanese telescope, the infrared survey. So we would like to incorporate both of those telescopes into our network of telescopes as well. They have different capabilities, both in the near-infrared. Prime at the moment has an imaging camera, but it will also have a spectrograph, a high-resolution spectrograph. The main aim of the Prime telescope is to find planets around other stars, or actually even free-floating planets. And it does that through the microlensing technique. So Prime has a very big field of view, can observe 1.5 square degrees in one shot. And that makes it quite fast for surveying. And so the idea is to survey the galactic bulge. So here you can see the center of our Milky Way galaxy. There's a lot of dust there, and that obscures the starlight. And that's why you have to go to the near infrared, which can, to some extent, peer through that dust. Survey of our galaxy. And the idea will be to look for changes in the brightness of starlight. So it'll image the galaxy over and over and over again, and any changes in the brightness of a star it will pick up. So here you can see if there's a distant star, the light from that distant star gets slightly brightened by the gravitational lensing effect. So this is like having a magnifying, the star in front acts like a magnifying glass that slightly brightens the star in the background. So here you can just see how the brightness but if there's a planet going around the foreground star, you get an extra little blip here on the light curve, and that can be detected. And so that's the signal that they're looking for with Prime, to try and find planets around other stars. I think there are about 80 planets found so far with this microlensing technique, and it's very complementary to other techniques that find exoplanets. So you may know about the radial velocities, that's what I talked about before, that SALT's HRS will do. You may have heard about the TESS satellite or the Kepler satellite. Those look for transiting events where the planet passes in front of the star and the starlight dips slightly as the planet passes in front. So this one is a complementary method. And PRIME will also be very complementary to the Roman Space Telescope, which is due to launch next year. The planets that this method is sensitive to are the ones that are a bit further out from the star, so sort of from Jupiter's distance from the star outwards. So Jupiter's and Neptune's, those kind of planets, but also going down to lower mass planets like Earth mass planets that are a little bit further away. And then with that information, you'd be able to get a more complete census of the types of planets that have formed around other stars and learn about planet formation. So in addition to the exoplanets science, at SAAO, we also do various other kinds of research. So a big one at the moment is transient astronomy. So that's looking for changes in light, anything that's changing, stars that are exploding like supernovae, the types of the counterparts of gravitational wave events, any kind of change detected in the night sky is what we refer to as transient astronomy. So it could also be the black holes in the centers of galaxies that are changing the amount of light they produce over time. And that's a big focus area. We have sort of more traditional stellar astronomy, studying the stars and how stars formed and evolved. We have extragalactic astronomy, which is looking at those groups of billions of stars, how the galaxies themselves formed and evolved over the universe's history. We have some people looking at the AGN, or active galactic nuclei, the supermassive black holes at the centers of galaxies. We have a small group looking at asteroids, and this is an example of an observation of the DART mission. So this was a NASA mission that basically collided a spacecraft into the moon of an asteroid. NASA collided the spacecraft into that to see if they could deflect the orbit of the asteroid. And as it collided, it let up this plume of material, which we observed from Sutherland. So they were actually successful. They could deflect the asteroid slightly. And that's probably the technique that will have to be used if we find an asteroid that's going to collide with Earth to prevent that collision. I talked already about astronomical instrumentation. So the instruments that we develop are also require research into the best way to develop those instruments. So that's also part of the research that we do. Then another recent project we're very excited about is called the LSST, the Legacy Survey of Space and Time. And this is a project based at Observatory telescope. It's an 8.4 meter telescope. You can see the inside. And South Africa is involved in this project. So I'll tell you a little bit about how South Africa is involved in it. But the Rubin Observatory celebrated its first, and so that's why it's a very exciting time. And they're going to start a 10-year survey towards the end of this year. So this telescope, although it's 8.4 meters, the mirror is 8.4 meters in diameter. It's very, very, very big, but it very quickly, they can get onto the target in about 5 seconds and then change and observe something else 5 seconds later. So that's incredible. I think just the camera is about 3 tons. I don't know how heavy the telescope itself is, but it's incredible that it can move this fast. The biggest camera in the world. So here you can kind of get an idea of the size of the detector relative to a person. It's 3,200 megapixels. And the image that camera takes would need about 400 TVs to use the full resolution. So it's a huge amount of data each time the camera takes an image. The Legacy Survey of Space and Time will image the southern sky, the whole southern sky that's visible from Chile. And it'll take about 1,000 images a night. And so that's an enormous amount of data with such a big camera. It's about 20 terabytes a night. And I think I heard that that's about the whole of Netflix that you could watch in 3 years in one night. Over the 10-year survey, that adds up to about 60 petabytes, or so 60 times 10 to the 15 bytes of data. That's an enormous amount of data that it's impossible for anyone to actually download that data and work on it on their computers. And so what will be done is they'll serve it through their platform. So you'll be able to actually cloud system and then download what you need to, or the results of your analysis. So it's a different way of working to what we used to. The field of view is equivalent to about 45 full moons, so a 10 square field. And that enables them to do this survey very fast. So they'll, over this 10-year period, they'll basically do a time lapse of the whole southern sky, and basically take a movie of the southern sky with 30-second exposures in 6 different filters, so covering the whole optical range. And with the survey strategy they've decided on, they'll come back to the same patch of sky about every 3 nights. And then they'll be able to see in that new image if anything has changed. And they expect to find about 10,000 transients in each image that they're taking compared to the previous image of the same spot. So many, many, many new objects being detected all the time, about 10 million alerts every night. And those alerts will be public within a minute after the data is taken. So they've set up the software to find any differences in the images and put out those alerts so that we can follow up those objects from Sutherland or anywhere else in the world. The trick will be trying to figure out which ones are interesting. You can't follow up 10 million objects. So how do we know which ones to actually take further? And that's where we'll have to use things like machine learning to find the best way of handling all those alerts. So South Africa is involved. We've made contributions by providing time on SALT, by providing time on the other SAAO telescopes. And that's mainly through one person, Michelle Lochner, who's based at UWC. She's been very involved in the collaboration, the dark energy science collaboration of LSST for about 10 years now. And she's contributed hugely to designing this, to plan the observations to get the most out of it. So she's one of the sort of survey builders. And then there's also someone at WITS, Matt Hilton, who is, he and his team are reducing meerkat radio images to So with those 4 different contributions, South Africa has been awarded 10 PI positions, principal investigator positions. And so we have 10 principal investigators at universities all throughout South Africa, and each of them has a group that can have up to 8 affiliates. And so we have up to 80 people across South Africa that can work with the LSST data, and they have full access to the data in the same way that the American and Chilean survey members have. So the topics that'll be studied from South Africa include that transient astronomy, so studying these changing events, galaxy formation, AGN, and then Michelle and her group are looking at machine learning for finding anything interesting. So trying to pick out the anomalies in the data, and that can then be used to choose which ones to follow up. And just to give you an idea of the size of the data and the way that transients are detected, I just thought I would share this lovely movie from the first look of the Rubin survey. So here you can see a new asteroid being highlighted. Each of these circles is showing you a moving object going through the images. So these are all new asteroids in our solar system. And the first light images, you can see there the night they only captured about 6 nights of data that they presented as their first light. And in that time, they discovered more than 2,000 asteroids, 7 nights. So 1 week of data, 2,000 new asteroids that we didn't know before. This sort of band of asteroids going around the Earth, or around the sun, further out from Earth. And LSST just looked through that one tiny little patch of sky and found 2,000 of them. So that's the kind of data that Rubin will provide. And we're very, very excited to be part of it, to find these asteroids, but also to find all sorts of other transient events, to study the millions of galaxies that they're going to find, and many other science areas. Okay, so the Rubin Observatory is named the astronomer who discovered dark matter, or really highlighted the existence of dark matter. And so I thought it would be nice to just include this quote from her: "Don't shoot for the stars, we already know what's there. Shoot for the space in between, because that's where the real mystery lies." And the Rubin Observatory is really going to highlight all the things we didn't know about the universe, the asteroids, the new transient events. So very exciting time for us to be involved in this project from South Africa. And so I think overall we have a very, very bright future ahead of us in South African astronomy, and Southern Rubin Observatory take advantage of it. But many exciting new developments in South African astronomy. I just didn't even mention the square kilometer array and the radio, incredible radio project that's being built in the Northern Cape. And that is just one of the biggest science projects in the world. And South Africa is a major part of it, and the host of the square kilometer array. So African astronomer, and we're looking forward to what lies ahead. Thanks. So the question for those online is about galaxies, and if they're forming continuously, would we have new additions to our galaxy? So galaxies are forming new stars all the time. So they're growing by forming new stars out of the gas that's available in the galaxy. And our galaxy, the Milky Way, sun a year. So it's pretty slow compared to some other galaxies that are forming stars at hundreds of solar masses a year. But it is steadily growing on galactic timescales by forming new stars out of the gas that's condensing and collapsing to form stars. So that's one way that galaxies can grow. If they have gas in them and that gas is dense enough, they can form stars out of it. Another way galaxies can grow is through collisions with other galaxies. So the Milky Way, our galaxy, will collide with our neighbor Andromeda, and then it will end up, they'll orbit each other and eventually settle down into one new big galaxy. And so eventually that would basically double the mass of the galaxy, because Andromeda. So that's another way that galaxies grow, and probably the main way that the big galaxies grow, because they're not really forming stars at high rates anymore. Well, that much data. It's a good question. We have to develop the tools for it. The Vera Rubin Observatory will send their data from Chile to North America, and that will happen almost immediately. So the data transfer will be computing facilities available that store that data and then make it accessible to people. So it's a major challenge, and this is what we call we have a cloud computing facility, which is a partnership between the University of Cape Town, the University of the Western Cape, and the University of Pretoria. It's called IDEA, the Inter-University Center for Data Intensive Astronomy. And they have a cloud-based platform where students and astronomers around the country, and everyone using Meerkat data can log onto that system and process their data on that cloud rather than doing it on their own computer, because Meerkat is already producing much more data than we can handle on individual computers. The square kilometer array will be even worse, more of a problem. And so we have to build the tools to keep up, and there are people very actively working on that.
Communicates with people.
Yes. So is there any particular question about how we collaborate and
He's asking you, how do you manage?
How do we manage liaising with our partners all over the world and collaborating? Yeah, it does take up a lot of time. We have groups of people that that work with our partners. So, for example, we're part of the African Astronomical Society, and we have regular conferences with astronomers from elsewhere in Africa that come together and meet for a week and look at what facilities we have in Africa and how we can work together better. We have a BRICS consortium as well, a BRICS working group in astronomy. So those two are mainly actually run by the Department of Science, Technology and Innovation, with participation by all the astronomers. But then there are a lot of individual collaborations. So yeah, the Rubin Observatory, I'm the lead, the sort of project lead for the South African contribution, but we have a project manager and the individual principal investigators that actually do the work involved and are part of the science collaborations, the international science collaborations. Okay, so the question is, well, there is some collaboration between Sutherland and the South African Radio Astronomy Observatory that runs Meerkat. What about the James Webb Space Telescope? So we have a strong partnership with SAAO, who's our sister organization under the NRF, the South African Radio Astronomy Observatory, and they're based just 5 minutes away from us in Cape Town. So we work quite strongly with them also on technology development. Then in terms of international projects like JWST, we have individual astronomers who are on JWST proposals or have themselves proposed for time on it, and then are analyzing that data either with a local group or as part of an international collaboration. But we aren't directly involved as an organization in JWST. Yeah, so the question is about as a young person getting involved. I think how do you start, and do you need to follow artificial intelligence as part of your career journey? Yeah. Okay, so the concern is that AI is taking over, and is there still a role for people in doing the research in the future? There is definitely a role, and it's I think, although we think that artificial intelligence will take over a lot of the kind of more menial tasks and sorting through that huge amount of data and maybe pointing us in the right direction with that large amount of data, you will always, I hope, need the astronomers to actually teach the machine, and also, ask the right question, and figure it out. So there's been huge development just in the last few years with artificial intelligence, but it's not at the stage yet where there's something that can run off and do the research on its own. There's definitely a huge need for clever people who can use these as tools in their research. And I think if you study astronomy on the way, you would learn the data analysis techniques, the coding, the communication, those kind of tools that would stand you in good stead in many different careers that South Africa really needs. Even if you don't end up actually doing astronomy research, there are many other options for you if you study astronomy. Yes, so the question is about the lighting, particularly in Sutherland, and whether there are ways of keeping the light facing downwards rather than up. And so that is what has to be done. For example, with the new lights put up at the clinic, As soon as we realized that masts were going up, we contacted the developers and discussed with them how they could mitigate against any light pollution, and that it's only going downwards, not being scattered up into the atmosphere, and much dimmer than they had originally intended. Another option is to use motion sensors so that it's only the lights are only on when there's movement. So we have to liaise with it. We're working quite closely with the municipality because there are, there's the school, hostel, the street lights in town, that they could all be improved. And yeah, definitely the light fittings could be changed to be better for us. So we're working with the municipality on that. And I think it requires constant education of the people who live in the area, that they don't have spotlights for security facing upwards, but face them down. There are definitely things we can do. So far, the question is about the Starlink satellite constellations, whether they're a problem for us in the optical part of the spectrum. So far, they haven't been a big problem for our telescopes in Sutherland, because our field of views are usually relatively small, and the satellites are mainly early evening and the morning twilight. So we haven't been very strongly affected so far. But as you get to these larger field of views, like the Rubin Observatory, I mean, they're observing such a big part of the sky that there will definitely be satellite trails affecting their images. And so they're working quite closely with the companies, with the International Astronomical Union, to try and get these companies to make their satellites darker so they don't reflect as much light, to sort of alert them of the satellite paths so that they can actually not observe it, in a satellite pathway. So there are things that are being done to try and mitigate against it. So far, we've been relatively unaffected in Sutherland. Every now and again, you get a satellite passing over and ruining your image, but it hasn't been a major problem for us. Yeah, so the question is about the probes that go to other planets and moons in our solar system, and whether SAAO is involved in those projects. We aren't directly involved.